My presentation today is deals with Boolean functions, vectorial functions. Okay, I will discuss also non-Boolean functions. And the title of my talk is Read Digits of 17-year achievement on Boolean and vectorial functions and upper problems. First of all, I would like to thank the organizers for this outline conference deeply. I thank them deeply and express my happiness for this kind of invitation. I confess that I would like to, I would be very glad to give a talk on, not online, but in Italy, a country that I love too much. And they have a lot of friends also. But I fully understand the difficulties and the different constraints. So during the 17 years, I have worked on different aspects of functions over finite fields, including the crucial case of Boolean and vectorial functions. The case of the Boolean case, I mean, in classic 2, it is has much importance because it's in real application nowadays. And also discrete mathematics for semantic cryptography for more general things and the coding theory. And in this talk, I will start naturally by recording some background on functions over finite fields, the cryptographic framework of Boolean functions. And during this talk, I will present some mathematical achievements on various topics related to Boolean function obtained since 2007. I will give an overview on the mathematical problem, the obtained results, and the remaining open problems. Of course, I am exciting on about providing many open problems. Many of them you'll see are not too much known. At the end, you'll see that there are more problems related to in which we are interested nowadays. Let P be a prime and Q is the power of P. Namely, and I take R is a positive integer, and I consider the finite fields Fq to the R. So I take the power of P because to build Q to have a finite fields. And so I construct the finite fields of Q to the R elements. And I consider the trace, okay? The trace from Fq to the R to Fq. Of course, the trace is the sum of the conjugate of X, where X in Fq to the R with respect to the field Fq. So this sum, X plus Q, X to the R minus 1. And in the case when Q equal is prime and the output set is the field subfield Fp, the prime field Fp, we call this trace absolute trace and not the relative trace. The first is the relative trace, absolute trace. This is a very, very interesting object. Why? First of all, with this trace, I can construct, of course, I can define a scalar product. Why I need a scalar product? In many cases. For instance, to define the Fourier transform and the Ward transform, etc. I need a trace function to define. It is not an obligation, but it can define a scalar product and can use it can be used in to define the Fourier transformations. In the case when the function is of a function, when in the case the function is defined over finite fields, of course. And it also allows me to construct code words of codes, linear codes. And it also allows me to construct to consider components of vectorial functions. We'll see vectorial function is just Fp to the n to Fp to the m, and if I consider the trace, a special trace of Ax, where A is in the output set, it means to consider the components of vectorial functions. And so it is very, very important object, mathematical object, in which I will use this, we can use it to define functions, component of functions, and we will see that cryptographic property of functions are, vectorial functions are closely related to those of components. And to consider the components, I have to take the trace if of course the function is defined over finite fields. So I have Q with P to the R, and a vectorial function, so it's fq to the n to fq to the m, where n m to integer, and this is what we call also nm query functions. In the special case when q is a prime even case, p equal 2, we say simply nm function Boolean, and when m equals 1, we said it is a Boolean function. So a Boolean function is just a mapping from f2 to the n to f2. This is a very, very simple object. Inputs gives 0 or 1. It's very, very simple object, but we'll see that it is important object in coding theory and cryptography, and the related problems involving Boolean functions could be very, very, very hard and complex, etc. We'll see during this talk. So Peary function, which is a Peary function, is just a mapping from fp to the n to fp. So it plays an important role in first in coding theory. If you take the example of Reed-Muller codes, the element of Reed-Muller codes can be not you can, but it is not necessary, but you can view it as Boolean functions, Peary functions, in which the degree is at most some positive integer r, for instance. This is Reed-Muller codes of order r or of length p to the n. And so it allows me to construct, to define Reed-Muller codes, and allows me to construct also many codes. You will see with there is a general construction of codes which are interesting for applications in storage, in secret chaining, two-party computation, etc. Minimal codes, etc. And I can use those functions to construct codes. And of course, I can use those functions to construct important components in primitive in semantic cryptography. But of course, in practice we use the case when p is an even prime, so p equals 2, in the Boolean case till now. So when we say function, we say value and expression. So value, it is a if you take a Boolean function, the value is it's the value that that can take 0 and 1 is a table through table, and expression. So when we have to represent a Peary function. So if you identify the vector space fp to the n and the dimensional vector space f to the n with the finite fields fp to the n, this is very interesting because we move from vector space to finite fields, and the finite fields, of course, the Galois field is rich. Why it's rich? Because I use, of course, it is a vector space and the dimensional vector space over fp, but also I can define many objects, in particular exponential sums. I give just examples: chromosomal sums, cubic sums, etc. I can give many computation. Field is stronger algebraic structure. And so when we identify, so I see the vectorial function, the PRA function from FP to the N to FP. So how can I define? How can I represent? So first of all, the PRA function is just can be obtained by, again, go back to the trace, the trace function from FP to the M to FP of a vectorial function FP to the N to FP to the N, and you obtain your PRA function. So the PRA function can just obtain it by making a trace of a vectorial function from FP to the N to FP to the N. And we have a univariate representation, which is of a PRA function in terms of a trace function. And it's for degree at most the PPTN minus 1. But the negative thing is that this representation is not unique. And we want the unique representation. And there is another representation of a PRA function defined over the finite fields of PTDN called the trace representation. It's given in the slide number 5. It's you see my hand here, Norberto. When I show this, you see or not?
Yes, I see.
Okay. So it seems complicated. Read f at x, sum, blah blah blah, a trace, extra. But it's very simple. In fact, what is it? You take a monomial, a monomial function. So a power function, if you want, x to the j. You take the monomial function. So of course. You take the coefficient not equal to 0, otherwise it's the generate case. So a jx to the j. So it is a function from fp to the n to fp to the n. We take the trace function over fp, the absolute trace function over the prime field fp. The trace is not over fp to the n, but a subfield of fp to the n, namely fp to the power OJ. I will explain this. And so you consider this one trace, you add another trace. So you take power function, of course, monomial. You take the trace and you add a trace, etc. What is the difference between two traces? Is j. J is an integer, and it's ranging the set of integer obtained by choosing the smallest element. That is which we call usually coset leader. In each p cyclotomic cosets modulo p to the n minus 1. And we add this constant term effect. If x is not equal to 0, this is x to the p minus 1 equal to 1. So this is a constant term. Note that g could also take the value 0. So we have a constant term coming from here and here. And if x equals 0, this is 0, and we have only the constant term here. So f at 0 not equal always to 0, unless j at 0 equal to 0. So we have this representation. It's not complicated, but it seems very complicated. And so it is a trace over subfield of fp to the n of order over the finite fields of order p to the oj. What is OJ? Is simply the size of cyclotomic coset containing J. What is the cyclotomic coset containing J? You take, it's simple. You take the integer J multiplied by P, J multiplied by P squared, J multiplied by P to the cube, etc., and you stop when we get again J. And all the computation is computed modulo p to the n minus 1. So this is a cyclotomic cyclotomic coset modulo p to the n minus 1. And the set that you obtain, you count how many elements you have. This is the size is OJ. And so we obtain this representation so precisely. AJ belongs to the finite fields of FP to the OJ, which is a subfield of FP to the N. So OJ divides N, and the constant term here, AP to the N minus 1 belongs to FP. So someone can send me, how you can get why this trace, etc. The demonstration is a bit long. I will not give it here, but let me explain just the idea. You start from a vectorial function from fp to the n to fp to the n of a degree at post p to n minus 1. And we say that your vectorial function is a PRE function. So the output set is field is fp. So you write f in capital letter at x to the p is equal to f at x. So you write this, the univariate representation. You write the identity, f at x. If you can take the case when p equals 2, you write f squared equals f. This is mean that the f is the output set in Boolean, so in f2. And when we you have to make some computation, you have power, so you distribute, you make some computation, and with this condition, f p to the m and p equals to f at x, you obtain a necessary on sufficient conditions on the coefficient, so that namely the first one, the first one and the last one belong to fp, and the others coefficients satisfy a relation. And combining this relation, you make appears the trace function, and you obtain this representation. Okay. So this representation is very great because it's unique, and thanks to the uniqueness, existence, uniqueness of the pair function, we can define the degree. Otherwise, we cannot define the degree, and we can define the degree, which is the maximum PRE weight of J for which j is not to 0. So it is the number of non-zero entries in the PRE expansion of J. It's simple. Take J if you are in the Boolean case, P equals 2. What is the PRE 2-ary expansion of J? You take J is an integer. You write it as in the binary expansion, 0, 1, 1, and you count there is how many 1 there are. So this is and you take the maximum for each exponent J. So to compute the degree, we have to work. You cannot take it. Example: if J is in the form, I don't know, p to the n plus 1, what is the degree? Is 2? It's quadratic because p to the something, I don't know, p to the m plus 1. P to the m, there is 1 in the position PRE, and 1 is 1. There is 1 in the constant to the p to the 0. So it's quadratic. But there is some exponent who are very, very, very complicated to compute the PRE expansion. Even the binary expansion, it's complicated if it depends on n, etc. So how to compute? You have many traces plus and constant terms. You take J, you compute its PRE function, and which j is equal to 0 for each trace, for each power function involving the trace, and you take the maximum, and it is the algebraic degree. So the algebraic degree is not simple, and there is some error in some papers because the degree is not well computed. We can make errors because it's not simple. Okay, but if I go back to, if I do not identify fp to the n with the finite field p to the n, then I have what many people knows, the algebraic Raman form. The algebraic Raman form is a multivariate representation of PRE functions as so polynomial in variables in which the degree of each indeterminate is at most p minus 1. So in a polynomial form, in the finite fields, it is a polynomial when variables in which the coefficient belongs to subfield of p to the n. In the ANF algebraic Raman form, it is a function. It is a representation with the n variable as a polynomial in n variables. and the coefficient here belong to f2 in the case fp, sorry. So this is a I give an example in the case in Boolean function p equal to, and if you have a function algebraic degree in algebraic form, it's simple also to compute. It's simple, much simpler to compute the algebraic degree. In fact, it's sufficient to read. You can read it. The algebraic degree can be read. If I take the function x1 and 3 variables, x1 plus x2, x3, I don't know, plus 1, it's degree 2, etc. It is the algebraic degree is the total degree of each algebraic normal form. So okay, but what you have to do? I mean, in the finite fields we have representation, and the vector space we have representation. What is the best for our community to use for our motivations and in code and cryptography? Since the conference here is namely code and cryptography. So I won't say that you can choose what you want, but it depends on what you want to do. There is some problems in which you take the function. In fact, finite is much simpler because you can use Gauss sums, exponential sums. You can make decomposition, polar decomposition, representation, etc. And but sometimes in the vector space it's much simple when you study some cryptographic criteria, such that right, for instance, to the algebraic community or something like that, or resilience, etc. So it depends on what to do. You cannot. There is no best choice. Each one has its difficulty, and you have to choose and to look what the tool that you want to use. Of course, an important tool is the Warsaw form. This is magnifique tool, really great, in particular to quantify the cryptographic parameters regarding some when you use pair function in symmetric cryptography, for instance. Of course, it's also to allows to compute. Also, you will see not in this talk. Sorry, we can also compute the weight distribution of code words, in which the code words are constructed from functions. So it's a very important tool. Is the Warsaw form. What is the Warsaw form is given in this formula. It is you take zeta p is the primitive p root of infinity exponential to I pi over p. You take the function. You take the power function f at x minus the absolute trace bx. B is the input, and the function is fp to the n to fp. So this is the Warsaw form of f at b. What is this trace? What happened here? This is just a scalar product. B x maps trace over fp to the n of b of the product bx is scalar product, and it is an inner product in fp to the n. It consists with the canonical product in fp to the n. I write it here, and here you can make minus, you can minus plus. It doesn't matter, but you have to be careful, because if you use make plus here, with the Warsaw form has many properties. Warsaw form has many properties. In particular, you have the identities, possible identities, the identities, sorry, and many orthogonal formula extra using Warsaw form. So you be careful. If you make here plus, you have to be careful in the formula deducing involving the Warsaw form. And if p equals 2, here minus or plus, it is the same. Okay, and of course, if your function is over the vector space fp to the n, here is the product, the scalar product. You take two vectors of length n, and you do the scalar product the sum of bi xi, where bi xi are the components of b and x, and you get to the Warsh's form. Okay. Yeah. What I have to say is so let me go to the case, which is very important because it's practice cases, not because it's easy, because it's practice. And of course, many results in the pairy case, in the binary case, can be extended in the pairy case. But some of them cannot. I mean, you have make efforts. You have to distinguish between results. I mean, there are results in which the extension from the binary case to the pairy case is just adaptation. I mean, you adapt your formula, etc., your proofs, and it's okay. But there are many problems we cannot. I mean, it's difficult to go to the pairy case and the back also. I give an example. I don't know. Look, a linear complementary dual curves. If you take the binary case, it is in some cases is much binary linear code is much difficult than the pairy case, etc. So it is not always trivial to go to 2 to P, but sometimes it's trivial. Okay. So why I am interested in the binary case? Because for practice use. So I go back to the just because I need the Reed-Muller codes of order Rn is a length 2 to the n denoted by MRRn. It's a set of Boolean function and variables in which algebraic degree is utmost R. And of course, if you take R equals 1, you the affine function, algebraic degree plus 1 is affine function. And the affine function are important. Why? Because it is exactly the function that you want to avoid when you use Boolean function in symmetric cryptography. And something that you want to avoid becomes important because you want to avoid it. Huh? And also it allows to contact code words of Reed-Muller codes. And of course, Reed-Muller codes has linear codes, have a length, a dimension, and minimum distance. And this is the parameter that you know. So this is a Boolean function in codes, namely code. In symmetric cryptography, so they are played an important role, of course, in both scheme ciphers and block ciphers. And in scheme ciphers, you know, it is it's based on Vectorial cipher, in which you hide your plain text by adding byte by byte the not a random a pseudo-random sequence in which you obtain it by combination of LFSRs combined by a Boolean function, and you obtain your cipher text. And in block ciphers, you know, it is not exactly the Boolean function, but Boolean vectorial function. And the vectorial function, of course, are important. They are called in symmetric cryptography as boxes, and they play, of course, an important role, in particular regarding to the confusion. The confusion, you know, block ciphers, you know, in the block ciphers, and you have to produce a confusion and diffusion regarding to the principal state by Shannon. Uncle Shannon said that you have to this. So the S boxes has provides the S boxes S for substitution provides confusion if you a vectorial function, and so the component of vectorial function are of course a Boolean function. So Boolean function are in both. This is in stream ciphers. This is the combiner model. You know, LFSRs combined by the Boolean function. And I will go fast. And this is the filter model. You take one LFSRs and you take the inputs of several inputs of one LFSRs, and we apply your function. You apply your function, your Boolean function, and the output is the key stream, which will be added to the plain text to obtain the cipher text. And of course, you have those models, but we can show that those models are equivalent. But you can go from one to other. But the cryptanalysis, on those models, two models, by combiner model and the feature models, have not the same complexity. And there are parameters. So for each attack, you will see attacks. For each attack, there is a parameter on the Boolean function. So a criteria parameters. But it happened nowadays that we have a criteria, but not attack. But normally, if you have attack, you have a parameter which quantify this attack, the difficulty, and to say if it is how to choose your Boolean function to make the cipher secure regarding this attack. So and then you have to do mathematics. So to make the cryptanalysis is very difficult to implement. We have to pay much attention when choosing the Boolean function. Choosing choose is you have to follow several recommendations. Those recommendations are called cryptographic criteria. So here we have many cryptographic criteria. I need some of them here in this talk. We have, of course, your Boolean function must be balanced. It means that the Hamming weight is simple to define. It's the cardinality support, and the support is the x in f2 to the n, where n is the number of variable of the Boolean function, so that f at x equals 1. In fact, f at x is not equal to 0, but since it is a Boolean function 0 and 1, so it's equal to 1. So this is the Hamming weight, is the size of the support. And balanced means that the Hamming weight is equal to 2 to the n minus 1, so 2 to the n over 2. And this is why, because to protect the system against attacks, distinguished attacks. And here's another criteria related to the degree. We have to choose our Boolean function high algebraic degree, and this is because related to Berlekamp-Basset attack. We have another criteria. We have to your Boolean function should be very, very far from affine functions. Far. This is mean that I have to make to introduce a metric, and the metric that you use between the Boolean function and the Hamming metric, Hamming distance, which is defined here. It's the cardinality of the set in which f at x and g at x is differ. The value differ of f at x and g at x, and the f and g are two Boolean functions. This is the Hamming distance between two Boolean functions. So I will go more precise things here, because the parameter here is the nonlinearity. And there is another criteria related to attacks, correlation attacks, second-level attacks, and this attack is very important. The criteria 3 is very important for the filter model, while the criteria 4 is very important in the combiner model. And regarding to the attack of second-level attacks, our Boolean function, so viewed as a combiner function, should be M resilient. M resilient with the M large. M is an integer, and the resilient. This is we can characterize the resiliency in terms of the Worcester form. It means it can be characterized by the fact that f at x, the Worcester form, is equal to 0 for every x. I will go back to this. I will give the definition. In fact, it is yes, it can be directly characterized by the Worcester form. And we have the algebraic community, which is related to algebraic attacks, appeared in about 2006. And the algebraic community is simply the minimum of the lowest degree of any non-zero function, which is annulator of the Boolean function or of its complement. Complement means we add one. F, complement of f is f plus 1. And we have to have the criteria. So the parameter is the algebraic community. The attack is the algebraic attacks. And the criteria is that the algebraic community should be high. And of course, when we say high, it does not make sense. I mean, high, what does it mean, high? You have to give an upper bound and say the high close to the something. Okay, so there is a many advance in this topic, and it has been shown that the highest value is n over 2, if n is even, or n plus 1 over 2 if n is odd. So the integer value of n over 2. And of course, there is unfortunately, it is not enough. We have to make attention of also fast algebraic attacks, which are because algebraic attacks are not enough. You have to take also algebraic attacks. You have to define another parameters, the so-called fast algebraic community. And there is there is a definition, of course, but it's still. I would say it's still a discussion because and it's not very simple to define. Of course, if you have many parameters, the problem is, first of all, and why we are working all of us hard, because we know that we cannot have all the criteria at the optimal value. So we have to make a trade-off. Trade-off between those criteria. For instance, just an example, if I want criteria 3 at the optimal case, I cannot obtain criteria 1 because I cannot have a maximum algebraic community, maximum linearity, and balance it. We'll see in a few minutes. So there is conflicts between some criteria. There is and each time we add a criteria, we have to start from the beginning, I would say, because we have to beginning. I mean, you have to study the relationship with your new parameter with the others. So what does it mean, relationship? Bounds. If I have this this parameter is high, what does it mean in terms of the other, etc. So there is a lot of work. I mean, and if it's simple, we can close and that's it. But there is a lot. So what is in the case of a Boolean? Boolean vector function. I insisted this because it's practice. So we have the linearity. I will see that it's the minimum Hamming distance between a and the Boolean function and the affine function. So affine function are functional algebraic degree at +1. And we can generalize linearity on the higher order linearity. So it is not the minimum distance between the function and the algebraic degree at most 1, so affine, but at most are, why not? It's the higher order nonlinearity. We have also, so we have seen the correlation immune and the resiliency. The difference between both is that the resiliency, we add the balanceness to correlation immunity. You have the algebraic community and fast algebraic community. And that you have also, and all this can be extended in the vectorial case. We can define the linearity of a vectorial function, we can, etc. And also you can define the something special for a vectorial function and not a Boolean. In particular, when we look at attacks, not in the on the seam ciphers, but the block ciphers. So we know the block ciphers like yes, yes, etc. We have generic attacks, differential attacks, linear attacks, etc. Boomerang attack, which appeared in 1999 by David Mesnager. And of course, we have attack, so we have parameter, and we define the criteria, and after that we look what you can do with your function, how to construct. So differential uniformity is a new, not new, but it is not new. This one is not new. It's a parameter related to which quantify the resistance of the vectorial function in symmetric cryptography. Mathematically, we say vectorial function, but in symmetric cryptography, we say S boxes. So regarding to differential attacks, and you have a boomerang uniformity, in which it is a tool. It is a tool to quantify the resistance of your vectorial function S box regarding to boomerang attack. And of course, those parameters have been extended. You will see in the end of this talk. And well, in which we are interested here? We are interested in, first of all, you have a criteria. Okay, there is attacks, cryptanalysis do attacks, and you have criteria. We take, we try to consider a tool which allows me to characterize. So I say that characterize means that the F is sorry, has this cryptographic property if and only if blah blah blah. So blah 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 could be with the Warsaw's form, with something. So you characterize, completely characterize. So you identify how to understand more than the definition itself. Characterize. You have, after characterize, you have to construct. So design function. A design function, you know, by computer, it's hard. I mean, n high. You take a Boolean function when n equals 6, or 8. It is what is the cardinality? 2 to the Boolean function, 2 to the n, 2 to the n. So it is double exponential. It's the number of atoms in the universe. It's impossible by computer. So we need, so you need computer to, of course, to handle small cases for small values of n, but you need mathematics. You need mathematics to construct. You cannot obtain by random your construction. No, it's not possible. So you have to think constructions. A construction, so to use the representation, and you see in the polymer form, you see which kind of G you have to use, so the exponent of the power function, and you can test some computation with by computer. I did this to define some hyperband function, etc. And after that, of course, we want to classify. This is in the same. So when we construct, of course, the problem is it new or not new? Your construction is new or not new? How to answer to this question? It's related to some high of the classification. It is if it is there is equivalence relation. Yeah, equivalence, fine equivalence, CCZ equivalence, that you know, etc., which allows you to know to identify if your construction is new, so it is equivalence or not equivalence of a function which has been already provided in the literature or not. It's very hard. We know in general how to compare with some generic construction like Mayer and McFarland constructions, etc. But in general, we don't have general method which works for any function, Boolean or vectorial function. So what we want to do, of course, classification, and sometimes you want to enumerate how many functions you have having this property. And of course, you want to, when you have your function, you have to connect this domain with another domain. You can connect with coding theory. There is a, I wrote a chapter on this, a long chapter, 100 page, on how we construct code from vectorial and Boolean functions and the PRE functions and etc. So connect this with the other domain. So codes or combinatorics, different sets, finite geometry over polynomial, etc. So in general, we went and when we make connections with when you have something in your domain and you make connection with another domain, it's great. I mean, you cannot be happy then with such a result. It's a great result. I mean, connect things which together each other and go to from domain to another one. It's rich and it's rich for all life and for all who will. For all the life, I mean, we read in, I don't know, 100 years after us, extra, if you survive from this pandemic, of course. Okay.
CM.
Yeah.
CM. Sorry, can you conclude in 10 minutes, please?
Okay, 10 minutes. Okay, I'll try. Okay. So,
okay,
we have, okay, as a code you can construct, of course, because it comes from directly from the definition. Minimal codes, I think that Martino discussed minimal codes for circuit sharing and two-party computation. Locally recoverable codes for storage can be defined using polynomial, which have very, very, very strong properties, such as that good polynomial introduced by in particular by Berg, but who is I forget his name. He's great. Okay, I forget the quote of Alexander Berg from Israel. Okay, and you can construct locally linear complementary job code, etc. And of course, we can you have your cryptographic function. You can consider vectorial case. You can extend you take p equals prime but odd, and you can construct a generalized function which are function in which the output set is the set of integer modulo a power prime. So if I take the nonlinearity. The nonlinearity is a parameter regarding to the linear approximation, linear attacks, etc. We correlation attacks also. You define the nonlinearity, so you can it's a minimum distance between two different functions. You can express with the Mortos form like this. And thanks to partial value identity, which is a array which says that the sum of the square Mortos form is equal to 2 to n, we can obtain a lower bound on the maximum value of the Mortos form, also an upper bound of the nonlinearity. And the upper bound of nonlinearity is upper bound for Boolean function, upper bound of to the n minus 1 minus to the n over 2 minus 1. And the function achieving this upper bound with the equality are called the band function. And you know that band functions have a lot of applications in many several aspects. It's external combinatorial object in many areas of application, codec theory, sequences, cryptography, etc. And they can be defined characterized simply by the Warsaw form. You have to look at the Warsaw form, stick these two values, it is band. And we can consider also a subclass of band functions. Hyperband functions are very complicated to design, but we have very results in obtained in 2020, or super classes of band functions, which are the plateau functions. The drawback of a band function in symbolic cryptography is, of course, the fact that the Warsaw form cannot be takes the value 0 at 0. And this is mean that the function cannot be balanced, and they cannot be directly used. So you have to modify using the article and the result of Hans Dubertin in 2006. And so what approach you can use? You can use tools of Warsaw form, polynomial over finite fields, Dixon polynomials, involutions. There is many evolution obtained. Very, very important as boxes, permutation polynomials, 2 to 1 or more generally to E to 1, 2 to 1 functions. You can define functions over finite fields, symmetric, quadratic, tools from algebraic geometry, curves, elliptic curves, algebraic curves in general, geometric finite geometry over polynomials, which are directly related to new band functions. Of course, you use a linear algebra where your function is defined in particular in the vector space, and the group theory when we define your function over there is results now on group theory. If you take the function defined of a group finite group, you use a tool for combinatorics. Even I wouldn't to show you, but I don't know if you have time. And of course, arithmetic number theory. Okay. So yeah. I have not too much time, I think. So if you think, let me. So I have a. You have my slide, okay? You have my slide. That you can ask me questions. Anyone you want, anytime you want. I give a lot of problems. I will just take the few minutes that I have to discuss, since I have introduced the nonlinearity. So the R or the nonlinearity is the distance between the function and the Boolean function in which algebraic degree is at most R. And we can, of course, be interested in the bound on or design of a function of higher R order nonlinearity with given another parameter, for instance, the algebraic immunity. Or you can consider what is the maximum value of the R order nonlinearity. And this is closely related to so I will skip this, to the covering radius of Reed-Muller. And of course, it is covering radius of Reed-Muller play an important role in particular to measure the maximum error to be correcting in the context of maximum likelihood decoding. And we wanted to how to compute the covering radius. So what is the covering radius? It is the maximum nonlinearity. So the maximum minimum having distance. And because it is max min, it is very difficult to handle. So we don't know in general how to compute for this in some cases. For R equals 1, it is partially open. And when R equals 1, greater than equals 1, we have an upper bound, which is actually the best upper bound. It is the upper bound of the covering radius of other Reed-Muller of other R of length 2 to the n. It is an improvement of Cohen and Litzin result obtained in 1992. And now we have till now the best result obtained with Carlet in 2007. And we tried, and the proof is what we have considered some sums, SSX, SK here. We take the ratio of consecutive expression SK plus 1 over SK. And we prove that when R is equal to 2, the covering radius of Reed-Muller of other R equal to of length 2 to the n is upper bound by this quantity. So finding an upper bound here, it's a month to find a lower bound of this ratio. And this we have to find the lower bound of the ratio, SK plus 1 over SK. We have to decompose this SK in sum of characters. You have to lower bound each sum of character. You use the characterization of the code words of Kasami, Tokura, and Zomi, and to lower bounding and the sum of character, and then to this is the third step is easy. It's just you use argument of monotony to lower bounding the ratio SK plus 1 over SK, and then you obtain your upper bound. The problem is that here, number 2 is that we don't know enough about the code words of Reed-Muller in general. So what we know in fact the calculation has been done for the code words having Hamming weights at most strictly 2.5 the Hamming the minimum Hamming distance of the Reed-Muller codes. And with my colleague from Russia, Alexei Oblakov, we have provided classification of code words of 16 and 18 because it was missing in my work with Claude of Reed-Muller codes of order n-3 and to the n. Why n-3? Because it's the dual of 2 or Reed-Muller codes of order 2. And it's a paper of it's not published yet, for about 40 pages about the algebraic description of those codes of 16 and 18, and which allows us to count the number of such code words, to enumerate them explicitly. But the news is that it was not enough to improve the covering grids of order for Reed-Muller codes of order 2 and led to the end. Of course, I discuss over 2, but for other r greater than 2, it is you use the recurrence formula, inequality between the covering grids of r plus 1, etc., and you get all the results, the upper bound on other r. It can be generalized. So the important point is to improve the covering grids of order 2 and left to the end. So I start now. So for further improvement.
Yeah, I must really ask you to conclude.
Okay. So I conclude. Okay, I conclude. So there is you have my slides. My name is Seminario, and my emails is given in voilà, in the web, or Maximiliano can give you my email. So what you want to conclude? There is a tons of work and the Boolean function, many exciting problems. Many of them are, some of them are not known, and but that comes from published results. But maybe 10 or 12 years ago, and they are on the slide, and you can ask me a question if you want. There is, of course, a main reference of the recent book of Claude Carlet on Boolean function for cryptography and code theory, in which he focuses on the case when p equals 2 in the Boolean case. But nowadays, there is what we are interested nowadays in construction of linear codes from cryptographic S-box. You have here a certain the chapter of the handbook, and of course in Semitic cryptography in S-boxes we are interested in, namely in differential uniformity and boomerang uniformity, in which the goal is to count how many the number of solution of an equation or a system of equation, in fact. And this come from this notion have been extended in C differential uniformity and C boomerang uniformity, where C is an element of the output set of the vectorial function. And the main idea is to modify the derivative f at x plus a plus f at x equals b in terms of the C derivative. In fact, there is a modification of the derivative in direction of a in another in more general things. So we have parameters, but the problem here is that we don't have an attack case yet till now, and you have to perform C differential uniformity and the boomerang attacks. You have to evaluate C differential and C differential uniformity for there are many results, but to generate more cryptographic classes, you have to study the relation between both in particular defined both in the subfield, which for instance, you can modify the inverse function it's used in the AUS and see the inverse function in the subfield of f2 to the n, in practice n equals 8. Study the relationship between those parameters with other classical that I presented in this talk. And of course, you can also take care about the cryptanalysis of such an attack and fault attention injected attacks in which there is also a parameters which appear, and you can make a nice project here in this side, in this last open problems. Okay, thank you so very much. I couldn't imagine that I speak slowly, but okay, I was excited to give many things, but okay, I hope that at least you enjoy what I said. Thank you so much.